I hope you're all doing well. Do you see these slides and hear me okay?
Yes.
Great. So, like you heard, I'm going to just take a few minutes to talk briefly about my kind of academic trajectory since leaving University of Florida. But I'll be honest, it's a pretty standard academic trajectory, so there's not a whole lot exciting there. I think I'll spend more time talking about the title of this talk, kind of the urgency and the challenges for scientists interacting with policymakers and the broad public. So, like you heard, I got my undergraduate degree in physics at the University of Florida in the mid-90s, and then a Ph.D. from Harvard University, also in physics. Um, Graduated in 2001. I then did an extended postdoc at the University of California, San Diego. I was there for 5 years, and I basically retrained as a neuroscientist, developing and using physics and optics-based tools in order to study function and dysfunction in the brain, with a focus on studies in animal models. I then started a faculty position 20 years ago in the biomedical engineering department at Cornell University, and I run my lab here jointly with my partner Nozomi Nishimura. When I was a grad student, I worked on on studying the interaction of very short pulses of light with transparent materials. Normally, the interaction with light with a transparent material is pretty boring. It just kind of goes through it. But if the pulse is short enough and tightly focused enough, you can get deposition of energy through highly nonlinear absorption. And that can produce some of the damage spots that are shown there in glass in the lower left. And I eventually developed applications of this in the 3D writing of optical waveguides shown on the right, by laser-induced damage to transparent materials, to glass. As a postdoc, I used similar kinds of laser ablation technology, except now instead of trying to use it to create little damage spots in glass, we used it to cause injury to the cells that line blood vessels inside the brain of a rodent. And just like when you cut your hand, that injury triggers clotting. The same thing happens here. If we injure the endothelial cells that line a blood vessel in the brain, we can trigger the endogenous clotting cascade and lead to the formation of a clot. The reason this is interesting is that while very large stroke, where you get an occlusion in a big blood vessel, is devastating, it's fortunately a somewhat rare disease, and one that we can create in an animal by tying off a big blood vessel, middle cerebral artery or something. They then have a stroke that looks a lot like human strokes, so we can study the mechanisms that lead to injury of brain cells and try to develop therapeutic strategies to improve patient outcomes. With very small strokes, it's not so easy to model them. So if we inject beads or preformed clots, we don't know where the stroke's going to form. And so it becomes a needle in a haystack problem just to find the stroke, let alone to study how it affects health and function of brain cells. So this method was really one of the first techniques available where we could cause the occlusion of a targeted small blood vessel in the brain of a rodent when and where we wanted, sort of shown down on the lower left here. And then we and now others use this model of small stroke, if you will, to study how these strokes impact the health and function of brain cells. On the right, for example, showing how occlusion of a blood vessel leads to rerouting of flow through the vascular network. I now run for the last 20 years, I've run a research lab again at Cornell with my partner Nozomi Nishimura, that's continued to build on developing and using these kinds of advanced optical tools to study healthy and disease state, function and dysfunction in the brain. This is an example of imaging of a couple of different kinds of neurons, shown in red and green, inside the brain of a live zebrafish, a small fish. And in this case, we use this targeted laser ablation to sever a single dendritic process that sort of extends up toward the top of the image there. We severed that dendritic process off of the red neuron without killing it and without injuring any of the surrounding green neurons. So this is actually modifying the wiring of the neuron of the nervous system in the brain of a small animal. And in this paper, we showed how that change in the wiring of the neural network leads to changes in the electrophysiological properties of the cells and their firing behavior. And that also led to changes in the behavior of the animal. So actually correlating wiring of neural systems and neural networks to behavior. Currently, we have a very large research effort funded by three NIH R01s aiming to try to understand the causes and the consequences of reduced brain blood flow in mouse models of Alzheimer's disease, where we've discovered that occlusion of small blood vessels, of the smallest blood vessels in the brain, capillaries, by the arrest of white blood cells underlies the blood flow deficits in mouse models of Alzheimer's, and that when we block that arrest, that improves blood flow and improves memory performance in the mice. Broadly speaking, I run a pretty big lab. We publish papers in top-tier journals focusing on a mix of developing tools and techniques for biomedical research, mostly optics-based tools, and then using that to elucidate the cellular interactions that contribute to function and dysfunction in the brain. I run a pretty large research group where up until recently, we were about three permanent research staff, 10 postdocs, 10 graduate students, and a small army of undergraduate researchers. So I'm going to stop there and see if anybody has questions or comments on kind of research background and this, and then I'll transition to talking a little bit about policy.
Does anyone have any questions?
I'm kind of curious. Yeah, I guess I'm kind of curious. The overall just transition from physics to neuroscience just sounds very interesting to me. I guess how did you know you wanted to make that transition?
So there was really so the question is about the transition from physics to neuroscience work. So there were really kind of three things, I guess, that motivated and helped facilitate that. One was at the time, there was a big push nationally from funding agencies, both NIH as well as private money, and kind of a push in the scientific community to bring more scientists with quantitative training in physics and engineering, computer science, to work on problems in biology and biomedical research. And this was motivated by the fact that there was an increasing amount of highly quantitative data emerging in biological and biomedical research. And there was a thought that folks with quantitative training might be able to bring unique tool building capabilities, data analysis capabilities, things like that to bear. So there was a real push in the field at the time for folks with physics educationists to transition into biology. And the sort of physics research at the time looked a little bit thin in comparison to the level of funding that was being invested into, for example, the NIH and things like that. This is during a time when it was policy of the US government to double the size of the NIH budget over the coming 10 years. So there was kind of a push for it. The second was towards the end of my PhD, we were pretty smart. We pretty clearly realized that this capability to produce targeted damage inside the bulk of a transparent material that we had developed, you could think of that as like a laser scalpel that could produce submicron scale cuts down inside a tissue without affecting things above it. And we thought that could be a useful tool for studies in for biological research, biomedical research, potentially for clinical applications. And I wanted to be part of the effort to try to make that happen. As you could see from the stuff I told you about, like the one thing that's been constant in my career has been my engagement with femtosecond pulses. So I didn't talk about my research as an undergraduate, but at the University of Florida, I worked in David Reitz's lab. He's now left and is at Caltech, where he was former director of the LIGO project. But when I was in David Reitz's lab, I worked on on building lasers and temporally shaping the very short laser pulses, which I subsequently studied the interaction of short pulse with transparent materials in grad school, developed tools to model small strokes as a postdoc, and use as an imaging and laser ablation tool now as a faculty member. So as I was transitioning from grad school to postdoc, I wanted to be part of the effort to try to bring that technology to bear in biology. And then the last was I found a research group that was a good place to transition. So I joined, my postdoc was with David Kleinfeld at the University of California, San Diego. David's in the physics department there, but his research is really um, much like my lab now, a bit of tool and technique development, and then using those tools and techniques to study brain function. So because David was trained as a physicist and was in a physics department, that was a good lab to kind of transition and to retrain as a neuroscientist. So it was kind of a career-minded choice, a scientifically minded choice, and an opportunity because of a lab that could facilitate that transition.
Cool. Okay, thank you. Yeah, it's very thorough.
Are there any questions on Zoom? Feel free to speak up. Or you can type it too. Well, what about here? Person? Oh. Okay, I think we can continue with your next part.
Great. So the main thing I want to take some time today talking about is science policy and science communication work. And this is both something that, folks could imagine transitioning to as a career, or regardless of your career, kind of an important activity or maybe obligation to be engaged with as a professional scientist. So first you might ask, well, why do I know anything about science policy? So about 10 years ago, I spent a sabbatical year as a AAAS Congressional Science Policy Fellow. So this is a fellowship that's been run by the American Association for the Advancement of Science for more than 50 years. And the idea is to place PhD level scientists as advisors in various places in government. There's about 300 of these fellowships, 30 or so that are associated with Congress, and then the rest with the executive branch of the government, where you would work in, the policy shop of NSF or Department of Commerce or something like that. So I had a fellowship that was funded by Optica and SPIE, the kind of Optics and Laser Society, and a fellowship to work in Congress. Sorting out which office to join is sort of like finding a research advisor. Could work for an individual member of the House and then a member of the Senate, or for one of the House or Senate committees that sort of covers lots of legislation. So I ended up working for Senator Ed Markey from Massachusetts. He still represents Massachusetts. I worked on a variety of issues, of course, science research funding and STEM education, but you pretty quickly learn in working in public policy that you have to be spread very thin. So there were a total of 6 people in Markey's office that, we were the entirety of the legislative and policy staff. So that included me. There were 6 people and we covered everything. So in addition to science funding and STEM education, I did a lot of work on nuclear power, nuclear weapons, non-proliferation and safety, a bit of work on privacy and technology, homeland security, cyber terrorism, variety of different topics. I often get asked why. Things are going pretty well in the lab. Why spend a year in DC? And I guess I've always been kind of an armchair politics wonk, but I think it's more than that. I think it's essential to find a good intersection and good communication between scientists and science and policymakers and policy if we're going to make smart decisions in a technologically complex world. So, for example, what is the appropriate approach for regulating the development of artificial intelligence systems? Science and technology innovation has been the dominant driver of economic growth globally. So learning how to harness that innovation in ways that raise more people out of poverty and give them greater ability to control the fate of their lives. The advanced society that we're developing is creating an unsustainable relationship between our society and our environment and climate. So figuring out how to mitigate that with improved energy generation, energy usage, and reduced environmental impact is critical. And then for my own kind of work, all kinds of discoveries about mechanisms of disease are not effective if they're not coupled with policies that help those mechanisms translate to treatments, and those treatments be given to appropriate people to treat disease. And just to give another example, I think good relationships between science and public policy and the public is necessary to guide public adoption of beneficial behaviors. So just to give you an example of this, so going back to the SARS-CoV-19 pandemic, this is plotting the probability of folks reporting that they were likely to get vaccinated as a function of time, kind of through the first winter of the pandemic, and is stratified by how likely folks or the amount of trust that folks placed in public health authorities. And as you can see, folks with little trust in public health authorities are quite unlikely to get this vaccine, while folks who place a great deal of trust were approaching 90% likelihood, self-reported likelihood for getting the vaccine. So dramatic difference in the likelihood of folks adopting a scientifically validated public health or behavior that would improve health. And this has consequences. This is some data from Switzerland, where they just happen to have really high quality data. This is now during the second winter of COVID, the 21-22 winter. And this is the plot of death rates as a function of vaccination status. The blue curve is fully vaccinated with boosters, and the black curve is unvaccinated, and there's more than 2 orders of magnitude difference in the death rate. So there was a lack of trust among public health authorities that was correlated with a decision to whether or not to get a vaccine that was correlated with radical differences in outcomes after infection with this virus. And so, I think it would be good if there was a minimum number of people on the unvaccinated line and a maximum number of people on the fully vaccinated line. And so the question is, like, what happened? Why? And in the US, adoption of the SARS-CoV-2 vaccines was quite a bit lower, and there's estimates of up to 1 million excess deaths in the United States that were potentially preventable by more early adoption of those mRNA vaccines. So I guess a big question then is, what happened? What's the problem? Is it that scientists aren't trusted? Or is it that what was being said, the public health message wasn't understood? Where does the problem lie? So what I'm going to do in the next 20 minutes is just kind of pour into some social science survey data, trying to get a handle on where the problem is. And then I'm going to pivot and just kind of give you my opinion on what I think the path forward is. So first of all, as scientists, we are an extraordinarily trusted group. So this is data from the National Science Board, asking public about their confidence in institutional leaders by selected institutions. This is from the United States. This is the United States of America. Military is preeminently one of our most trusted institutions, and that remains true. But in this data from 2018, the scientific community was next, well ahead of medical doctors, organized religion, banks, press, television, news, and certainly Congress, which is last. This isn't a new phenomenon. This is plotting folks that report a great deal of trust as a function of time. You can see there's some slip there for Congress and the press, and for financial institutions, especially after 2018. But trust in the scientific community, this great deal of confidence in scientific community has been steady now for 50 years. And this trust exists globally. This is rank ordered trust of countries. A trust index of 3.5, which is what this represents globally, is quite high. So this trust for the scientific community seems to be quite broad across the planet. However, we are currently living in an era of eroding trust. So this is a plot of the last 20 or so years in the scientific community, and this is the percentage of adults expressing some, a great deal, or hardly any trust in the scientific community. And at the very right of that plot, you can see a dip down in a great deal and a tip up in hardly any trust. And that seems to be quite real, and seems to have quite strong partisan leanings in the country. So this is percent of the public who say they have a fair amount, a great deal, or not too much, or none at all trust in scientists, here plotted as a function of time. And to the right, split out by folks who are self-reported Republicans or lean Republican, as opposed to folks who are Democrats or lean Democrat. So what you can see is that around the time of the SARS-CoV-2 pandemic in 20 and 21, there was kind of a step drop in the confidence that Americans expressed in scientists. That was evident in both Republicans and Democrats, although it was much steeper in Republicans. Among Republicans, it has not recovered. Among Democrats, it's gradually on a recovery trajectory. So I guess the takeaway here is that historically we've been a very trusted group. That trust is currently under some challenge, and there's partisan leanings to that lack of trust. People also care a lot about what we do as scientists. This is more data from the National Science Board, just polling people on what are the kinds of things they like to hear about in the news. And of these 10 issues, about half are very science and technology related, new medical discoveries, new inventions, environmental pollution, new science discoveries, ag and farm policies, and space exploration. I mean, new medical discoveries even beat out local school issues, which for parents can be, a life-shaping kind of news of something that's very salient to understand and know about. Again, this public interest in science has remained high over time. This is plotted for about 50 years, where interest in these various topics has remained quite high. Folks understand that science impacts their daily lives. These are folks who think that science, how often people thought that science impacts their daily life, either a lot, a little, or in orange, never. And you can see, like, during the pandemic, there was actually an increase in the number of folks who think that science impacts their daily life a lot. So science feels relevant and salient for folks. But there are some signs of challenges. So this is data from the National Science Board on public perceptions of scientists. Here from the 2000s, from some data from the 1980s, but much data from the 2000s through present. And what you can see is most folks agree that scientists help to solve important problems, that they work for the good of humanity, that they want to make life better for the average person. But if you look over to the right, currently about half of respondents would agree that scientists are odd and peculiar. And there is a pretty strong increasing trend over the last 20 years for that number to grow. This is borne out in other data. This is a more recent paper looking at the folks that agree that scientists are competent, quite high, trustworthy, high, honest, ethical, care about the well-being of others, all quite high. But it's not clear that folks agree that scientists share their values. I feel that scientists have a superiority complex, and they don't feel that scientists are likable. There does again seem to be some pretty strong partisan drivers of this disconnect. This is some recent data from the Pew Research Center, where everybody regards scientists as intelligent. But beyond that, there are partisan leanings toward the good that scientists do in community, with Republicans, for example, expressing pretty neutral opinion on whether we focus on solving real-world problems or are honest. Most agree that we are not particularly good communicators. And then when it comes to more difficult topics, you can see that even most Democrats don't regard us as aligning with our values, agree that we are cold and closed-minded, and those attitudes are highly prevalent among Republicans. So the kind of broad takeaway from this social science data, I would say, is that scientists are and have been trusted, but this trust is declining. Public cares about what scientists do, and they know it impacts their work. But scientists are increasingly viewed as odd and disconnected from other parts of society. So to me, this suggests a hypothesis, and I'm going to show a little data suggesting it might be true. But if scientists are kind of trusted in the abstract, but at the same time, they're viewed as odd and kind of disconnected from society, not sharing values, things like that, that's a kind of a shallow and maybe a very fragile trust. It's kind of a blind, abstract trust that's not based on substance or based on any personal connection. It's not based on a substantive understanding of science or scientists. And when scientists are viewed as kind of aloof and not sharing values, when a problem becomes really salient for somebody, really a big deal for someone, that trust in science may be just too fragile for it to influence their decision. And instead, they may turn to a more familial figure in their lives. And there's some evidence that this seems to be true. So with trust in science so fragile, other factors can influence attitudes, especially on controversial topics. So this is just kind of plotting in self-reported data in reports where people are asked, where do you get information or what factors seem to influence your decision making about particular topics. And you can see that, like, for example, on is the Earth warming due to human activity? Your political ideology or party matters more than your science education or science knowledge. For your attitudes about childhood vaccine safety, race and ethnicity is a larger driver of attitudes than science knowledge. So just to give you an example of where this happens, this is plotting the probability of folks answering some scientific questions as a function of something called the Ordinary Science Intelligence Index. I encourage you to look this up. It's a series of questions. The ones plotted here are examples of them, but it's some kind of scientific facts and principles, like, are electrons smaller than atoms, true or false? Which gas makes up most of the Earth's atmosphere? Nitrogen. There's some things about scientific methods, some things about quantitative reasoning, but it's a pretty good measure of knowledge of kind of ordinary scientific knowledge. So, and here you can see that things are as expected for people who don't have much scientific knowledge. They don't tend to get a lot of these questions right. And then you get kind of a sigmoidal curve that the the more science knowledge you have, the greater the likelihood of getting an answer correct. And some of these are quite hard. The lower left is, what is the probability that a woman who tested positive in a routine mammography has cancer? And there you actually have to understand something about prior probabilities and Bayesian inference in order to get the right answer. And you see that you have to have quite a good knowledge of science to get the right answer that the probability is small. The concern is the plot on the lower right. So here the question was, human beings as we know them today developed from earlier species of animals. And folks are broken out in their response based on whether they have above average in kind of yellow-orange or below average religiosity shown in blue. And as you can see, regardless of your kind of religious views, if you don't know a lot about science, you're not very likely to get this correct because you don't know a lot about drivers of climate change. For folks with below average religiosity, folks who know more about science tend to agree with the scientific consensus that human beings, I'm sorry, this is evolution, human beings evolved from earlier species. While folks with above average religiosity, as they have a greater understanding of an objectively greater understanding of science, they actually disagree more strongly with the scientific consensus. So this is what's often called motivated reasoning, where understanding more about the scientific arguments that are used in this case to underlie theory of evolution. If you fundamentally do not agree with the theory of evolution, having an understanding of that science allows you to fight it sort of in a little bit more coherent or in a level playing field, and folks tend to do that. This is not due just to a lack of understanding of the scientific consensus, though. So on the top left, I'm showing that same plot that I showed before. Human beings, as they know them, developed from earlier species of animals, broken down by below and above average religiosity, and that motivated reasoning is clear. The plot on the lower left is the same question, except preceded with according to the theory of evolution. And as soon as that precedes the question, then regardless of religiosity, people tend to agree more strongly with the scientific consensus as they know more and more about science. And a similar kind of trend with a question on the Big Bang. Religiosity is not the only thing that will divide folks like this and show evidence for motivated reasoning. So this is data asking folks whether there is solid evidence of recent global warming due mostly to human activities such as burning fossil fuels, broken down between liberal Democrats and conservative Republicans, again, as a function of the ordinary science intelligence index. And again, you can see that liberal Democrats will tend to agree with the scientific consensus as they know more science, while conservative Republicans tend to exhibit motivated reasoning and a decreased agreement with the scientific consensus. This is challenging because, I think agreement or acknowledgement of the scientific consensus is kind of an essential step in deciding on policies that could, impact things or improve things going forward. But here it's hard to know what to do. So if we teach conservative Republicans more science, we actually get less agreement between those conservative Republicans and the broad scientific consensus that would underlie any choice that we may or may not make to try to address global warming and climate change. So if more science knowledge actually makes things worse, what could help? So this data here on the left is what I just showed, probability of agreeing that global warming is due to human activity as a function of ordinary science index. And you can see that motivated reasoning among conservative Republicans. On the right, I've plotted this data as same people, but plotted as a function of a different scale called the science curiosity scale. Science curiosity scale measures different things. It's things like self-reported interest in science, time spent on science leisure, like watching science and nature documentaries or going to science museums, everyday discussions of scientific topics in a family with kids or things like that. So it's not about knowledge, it's about interest and engagement with science. And you see the same partisan split in broad agreement with the scientific consensus. But on the other hand, as the science curiosity scale increases, you see both liberal Democrats and conservative Republicans showing greater agreement, modestly greater agreement with the scientific consensus. So maybe tapping into this curiosity rather than focusing just on scientific facts and figures is one way to think about the problem. So what to do? I would say, the opportunity is the public is interested in and curious about science. And public tends to trust scientists and the institution of scientists, but we're really in danger of losing this. And I think the challenge is because for most people, scientists are distant and unfamiliar. In 2019, there was a survey done where I think it was more than 90% of Americans were unable to name a single living scientist. My understanding is that many more people could name Anthony Fauci during the SARS-CoV-2 pandemic, although many folks were naming Anthony Fauci not in a positive light, which he certainly deserves, but instead in a negative light. So the fact that folks can't even name, let alone know a scientist, I think leaves us feeling distant for most people. And in that case, other more familiar associations influence views, and more scientific knowledge in that case can actually just exacerbate motivated reasoning. So I think the thing that we need to do to try to address this is to tap into the curiosity the public feels and engage with the public about science in everyday life. And I'm just going to give kind of three broad buckets of things that I think that could help do this, and give some examples. So first, I think we need to tell better stories about science. Too often news stories about science are about sort of one whiz-bang discovery that, in 2 years, cancer is going to be cured. And, folks are smart and they realize 2 years ago, they read a different news article about how cancer was going to be cured and it's still around. And then it's not that journalists are distorting stories. It's really that these are the stories that we tell as scientists, probably trying to puff up our own work. But really, I think we need to talk more about how science and scientists work collaboratively and competitively over long times to solve problems. There was an excellent example of this. It's a little old, but from 2012, when the International HIV/AIDS Conference came back to the United States after being held elsewhere in the world for 25 years. It had been held elsewhere for 25 years because beginning in the Reagan administration, as HIV/AIDS was feared to become a global pandemic, there were visa restrictions put in place that would prevent individuals who were declared HIV positive from getting a visa that would permit them to enter the United States. And so the organizers of this conference were like, we're not going to hold an AIDS conference in the United States if people that are positive for the disease can't even come. George W. Bush, in one of several things related to HIV/AIDS that he did, began the process of unwinding that. And it was under the Obama administration that that rule was finally relaxed. And then immediately afterwards, this conference came back to the United States. And there was some excellent news reporting driven by the conference organizers around this, where they sort of said, like HIV/AIDS 25 years ago versus today. And the contrast could not have been more stark. In the 1980s, HIV had just been discovered as the cause of AIDS. It was the second of an entirely new class of virus called retroviruses or lentiviruses that had been discovered. There was very little understanding of how this virus worked, how you could stop its spread, how you could treat the disease. Folks who had AIDS, it was a death sentence and a terrible way to pass with really painful and brutal sequelae. The disease was spreading quite quick. There were no treatments that were effective, no vaccination schedules, approaches that seemed effective. Folks with the disease were ostracized from society, treated as pariahs. 25 years later, not only were lentiviruses well understood, but they were being used as viral vectors for the treatment of cancer. Modern antiretroviral therapies had effectively reduced being HIV positive to a chronically managed medical condition in the developed world. It's like having hypertension. It's not good for you, but you will die with HIV, not from HIV, if you stay on top of modern antiretroviral meds. Those drugs in 2012 were being rolled out into other parts of the world more quickly than any previously developed medications. They are showing incredible efficacy in bringing disease under control and stopping its spread. At the time, they were trialing vaccines that subsequently failed, but trialing them in Thailand. And folks with the disease served at the highest levels of government, academia, industry, sports, basically all endeavors. And so the news communication was, this is what science can do. In 25 years, with tens of thousands of scientists all over the globe competing and collaborating, with a $60 billion investment from the United States taxpayers and about another $50 billion in corporate and money from other places around the world, those resources used by those scientists can turn a death sentence into a chronically managed medical condition, and in fact capitalize on that knowledge to develop new ways to treat cancer. I think that's the kind of story that we should be telling, not stories about single scientific discoveries. Similarly, I think that would helping people understand how ideas that make it to news headlines, like methane leakage from power plants drives climate change. Folks need to understand that's not just one person spouting that gets accepted, but rather a lot of vetting and combination of ideas from many different folks before we get to that level of consensus. I also think we need to do more to tell stories about scientists as human beings. This was a great profile piece in the New York Times from a couple of years ago about Linda Zoll. I picked it just because she got a Cornell Ph.D. in civil and environmental engineering in the mid-70s. And during that time, she had worked on some of the first Earth-observing satellites. And because of that expertise, she was snapped up by the Central Intelligence Agency right out of grad school and worked for her whole career in the CIA, with much of it focused on technical aspects of satellites for spycraft work. But in the Clinton administration, Al Gore, who was vice president at the time, issued a call to all of government asking, if anybody had ideas about novel ways to use data or resources or other things that existed within the government that could be used to help understand and mitigate global warming and climate change, to please let him know and come forward. So Dr. Zoll wrote the vice president and got permission to go through and redact and declassify all of this Earth observation data that the CIA had from their satellites, which existed long before environmentally focused Earth observing satellites existed. And as a result, she was able to extend the historical record of satellite-based observations of deforestation, deglaciation, changes in land use, all kinds of things that would be interesting for folks studying climate change. She was able to extend that record back more than 2 decades. So again, an example of just a person responding to a call in government to make a huge impact. So I think we should tell stories like this instead of stories about our latest paper in Science or Nature. I think we should also provide better experiences for the public, not just hearing about science, but experiencing science, maybe being a scientist in the sense of making their own discovery, even if it was just a discovery for them, like maybe something that we already knew, but they discovered it. Imagine instead of learning F equals ma, imagine there was a series of experiments as open-ended as possible, as guided as necessary, where you discovered Newton's 3 laws of motion. And after that, you learn, about the dead white guy and the story of the apple falling out of the tree, and then the quantitative formulation of Newton's laws of motion. That kind of discovery could be a way that would build an appreciation for science that would potentially be long-lasting. There's also evidence that this is really what people want. I can tell you that the problems start really early. Up through middle school, on average, science is everyone's favorite subject. But that drops precipitously after middle school, and it drops more precipitously for individuals from groups that are traditionally underrepresented in the sciences and quantitative sciences, including women and minoritized students. If you think about it, middle school is basically where you transition from science being taught kind of as a exploratory process for discovery until it starts being taught as a collection of static facts in a book that you need to know. If you survey Americans about what they liked about science classes, most people say they liked it. 75% of people said they liked science classes. And most of those folks say they liked the hands-on learning experiences, the act of exploring and trying to discover things on their own, the act of sort of tapping into their own curiosity. So I think we can and we should teach science like this as a creative process for discovery as opposed to a collection of static facts in a book. But I think it's a lot to ask teachers to do this. If you, as a teacher, you don't learn how to manage open-ended experiments that could go in lots of different directions. You learn more about developmentally appropriate ways to interact with and teach children, through their learning process, all the way from kindergarten to 12th grade. We don't bother teaching college instructors how to teach. So I think the real way to do this is with partnerships between teachers and scientists, where a scientist can bring a comfort with the open-endedness of open-ended experimentation and discovery, while a teacher can help temper that with pedagogically grounded and age-appropriate ways to teach things. So for about 10 years, I ran a program here at Cornell called the Cornell Learning Initiative in Medicine and Bioengineering that partnered graduate students with local area K through 12 teachers for a year. Each graduate student and teacher partnership the graduate student would basically be a resident scientist in the classroom for the year, maybe visiting every couple of weeks, giving little lectures that helped connect things they were learning about in the classroom to research problems or real-world problems, helping to make labs more open-ended and inquiry-based. And then the teacher and the scientist would pick usually the part of the curriculum that the teacher hated the most. And they would take that and transform that into a part of the curriculum that was really where the concepts were really taught through as open-ended exploration as possible. And then the teacher and the scientist would implement that together. And then we published these ways of doing things. So I think this kind of partnership between professional scientists and teachers could be a way to dramatically improve science education, give people a more authentic experience of discovery, and change long-term attitudes about science. I think there's also opportunities in informal science education. I currently have a NIH-funded project with the Ithaca Science Center. They're a medium-sized science museum. We have a collaboration to build a museum exhibit on biomedical engineering targeting middle school students. And again, the focus is partnering graduate students with the museum exhibit creators to work on the design, the prototyping, the building, the assessment, and of this exhibit. We're in year 3 of 5 in building this thing right now. So we now have prototypes that we're putting out on museum floors and evaluating how children interact with it, what they learn from it, what attitudes, if any, change about their perceptions of science and scientists. And then finally, I think there's opportunities for real engagement with the public about science, listening to and respecting public concerns about science, and trying to communicate science ideas and their value. Some of this could be very issue-focused, one-on-one outreach. So I advise a group here at Cornell called the Advancing Science and Policy Group. It's a graduate student group of science and engineers who are focused on issues in public policy. During the COVID-19 pandemic, this group launched a program called Vaccine Conversations with Scientists, where we trained over 100 Cornell Ph.D. level and higher scientists, a lot about COVID-19, the SARS-CoV-2 virus, mRNA vaccines, the clinical trials, side effects, all the science that underlies that disease and the vaccines for it. But we spent most of the time teaching people how to have respectful conversations across difference, not try to be overbearing and data-driven and sort of scientific fact 1, scientific fact 2, so therefore you should do what I told you. So we taught people to be more sort of humble and more effectively persuasive in their interactions. And then we used kind of phone banking, tabling, door-to-door canvassing, and other kinds of things like that. This group had over 100,000 one-on-one conversations with residents of Tompkins County and surrounding counties during the COVID pandemic. And they showed that about a third of their conversations with folks who had not yet chosen to have the vaccine led to self-reported increased probability in them getting the vaccine. This group has recently found renewed enthusiasm in light of the less scientifically motivated changes in the childhood vaccination schedule that's come out of the Department of Health and Human Services. And so this has been converted into a local nonprofit here in Ithaca, and we are now primarily answering questions about childhood vaccination schedules for folks. I think citizen science is another fantastic way to engage folks in science. At the top here is just plotting kind of how many papers are being published by year that use citizen science approaches, and there's a dramatic escalation in that. I even have a little citizen science project called Stall Catchers. We have an image processing step in studying what causes reduced blood flow in mouse models of Alzheimer's disease that we have not been able to automate even with fancy AI-based approaches. But I can teach a human to do it in about 5 minutes. It's one of these pattern recognition things that humans are just really good at. And so there's about 35,000 people from around the world that have contributed to data analysis in now 6 or 7 published papers. And this is the primary path for analyzing this kind of data in our lab. So these stall catchers, we call them, are listed collectively as authors on these papers. So it's authentic contributions to the science. So those are just kind of examples of some things I think we could do: tell better stories, give better experiences, and involve the broad public in science. As you can imagine, all of that is sort of a tall order. So maybe I'll just talk about what are some very first step things you can do. One, remember, policymakers are effectively a distillation of the public. So engage with policymakers when things are happening in government that don't make sense to you. This is me writing my representative asking about funding to National Institute of Health. This is the letter I got back. It says no in just many words. But I think this kind of engagement is important. I think it's also important to participate in the political process. For example, I think it would be fantastic if at town halls and things like that during this congressional season, we had folks asking questions like the one I've written here. Given that a sound understanding of science and technology issues has become increasingly important for analyzing and acting on major national priorities, if elected to Congress, will you commit to hiring a PhD level scientist to serve on your staff as a personal science advisor? It would be great if that became the kind of question where your answer to that impacted how much people trusted you and whether or not they thought you would be a good person to represent them in Congress. I know that sounds far-fetched, but there's a more than 150-year-old organization in the United States that up through the 1980s mostly helped people learn to shoot firearms, I guess, more accurately and more safely. And then beginning in the 1980s, they made a deliberate decision to transform themselves into a more politically oriented organization that advocated for rights around the owning of firearms and different weapons. And this is, of course, the National Rifle Association. And for a long time, the National Rifle Association, their endorsements more or less determined who got elected to Congress for dozens of seats in the House and more than a handful in the Senate. So an enormous amount of political power, all centered on a really narrow political issue around acquiring and owning firearms. I think scientists have a better story to tell than the National Rifle Association. And whether or not you took science seriously could become a do you or don't you get elected kind of issue. It'll just take us making that case. I also think we should take efforts to inform our communities about our work. This past summer, some of you may have heard about this initiative. It's called the McClintock Letters, named after Barbara McClintock, who was a Nobel laureate who received her PhD from Cornell in the early 20th century. This was, again, led by this Advancing Science and Policy Club I advised, but we recruited hundreds of mostly early career scientists from all over the country to write op-eds and letters to the editor to the papers from the town that they grew up in. So kind of like a small town you grew up in, or maybe a small place you went to college, or things like that. We weren't aiming to publish in the LA Times or the New York Times or things like that. We were looking to publish in small local papers that are spread all over the country. So we recruited about 250, had about 250 op-eds published over the summer, where folks were describing the science they did and their connection to the community they were writing for, the potential impact of their work. And then we sent each of these op-eds to the offices of the members of the House and Senate who sat on the science appropriations committees. All of this happened around the time that those appropriations committees were considering science levels of scientific support in the fiscal year 26 budget. And as you probably all heard, in January, the final budgets that were signed include some cuts that will be devastating to some fields. But on the whole, are relatively flat, which is a huge departure from the Trump administration's request for up to 50% cuts in NSF, NIH, and other funding sources. So I think that's an indication, one, of both the broad bipartisan support for science, but also the effectiveness of campaigns like this that remind folks of what's at stake if science support is cut. If you're at Cornell, you could take my course in science policy, but you're not. If science policy is something that is broadly of interest to you and you're thinking about it as a career, I strongly encourage you to look into the Science and Technology Policy Fellowships run by AAAS. These are incredible fellowships, just to give you a sense of how important they are. So if you were in Washington, D.C., in a bar in DuPont Circle, which is kind of near where all the lobbying groups are, so if you were at that bar and you told some random strangers that you were a AAAS Science Policy Fellow, there's a 50-50 chance they would probably know what that meant, which shows just how much cachet this fellowship carries in DC. And so for folks interested in this, getting this fellowship can be a way to kind of, write your own ticket to what you want to do afterwards in the world of science policy. This work is really wanted, so I think we should get started. These are asking the public whether or not scientists should be involved in policy making, should advocate for policies, should communicate to politicians, be involved in policy making, and communicate to the broad public. And on average, this is strongly favored from Americans. This is something that the folks who are funding us and supporting our efforts want us to do, and something that, frankly, as a community, we're falling short in. So just to recap, I think we want to tell people what science has accomplished, or what science has accomplished is appreciated by policymakers and the public, but how we do it is poorly understood. Who we are is not well understood. And I think that is decreasing our effectiveness and our support. And I think the way to fix this is to really engage with folks. And that means doing more than just sort of being a sage on the stage talking about our work. It means much more authentic engagement and dedicating real time to this. This is not a whiz-bang solution. This is a long view strategy, but it's one that is associated with some of the greatest leaders in America who have faced much more difficult challenges and persevered. So Abraham Lincoln, presiding over the most tumultuous years of the United States, said, public sentiment is everything. With public sentiment, nothing can fail. Without it, nothing can succeed. And again, I think we have the sentiment here. And Martin Luther King, working from a jail cell, wrote that while the arc of the moral universe is long, it bends towards justice. And again, I think science is on the side of justice. So with that, thank you for your attention. I'd be happy to answer any questions.
Yeah, I mean, that was very inspiring to me, I think, but we'll open it up to any questions, either in person or on Zoom.
Yeah, I can ask one. So, could you give us kind of like an average day in your time as being kind of a science policy advocate?
So when I was, so you mean when I spent a year down in DC?
Yeah.
Yeah. So working in policy is a full-time job, more than that. So when Congress is in session and there's hearings and votes and those kinds of things, it was a 60 to 70 hour a week job. When Congress was not in session, it was a 50 to 60 hour a week job. In terms of what you're doing, it's changing all the time. During regular business hours from 9 to 5, it's lots and lots of meetings with constituents, lobbyists, staff from other offices, things like that, trying to understand issues, build consensus, fight against various things. That leaves getting real work done for either early in the morning or in the evening. And for better or worse, Congress is a very reactive body. So the first thing you did every morning was spend an hour reading a variety of newspapers and having an understanding of what's happened lately, because that could be very, very relevant to what you might do that day. In terms of the tasks, there's all kinds of different things. Some stuff's very reactive. There's a bill coming up. We need to look into it, make a decision about how we're going to recommend the senator to vote and why. There's a speech coming up. We need to, draft talking points for the speech. Some things are more kind of project-based, like this is a broad area of interest for the office. How do we, strategically think about moving this issue forward? For example, Markey's office has often been interested in the intersection of technology and privacy. The bill didn't pass, but in 2012, I wrote and we put in a bill that would have put regulations in place around the collection of personally identifiable information from drone aircraft that were at the time just beginning to be widely deployed. And that could have created a safety buffer that currently doesn't exist for both commercial and government uses of drones. So sometimes it's kind of project stuff. And then honestly, the most fun stuff was oversight work, where somebody somewhere in the world or in the country has done something bad, and you're going to call them out on it. That work was very interesting because it didn't require coalition building. A single office could sort of go after a particular problem on its own. For example, when I was in Markey's office, I played a role in very aggressive oversight of a program in South Carolina that was aiming to blend surplus weapons-grade plutonium into depleted uranium to make what's called mixed oxide fuel that could be used to make electricity in nuclear power plants. The problem was the plant required to be built to do this would cost so much money that this would be the most expensive nuclear fuel ever made, and it would be far cheaper just to blend it into glass and dispose of it like we do all kinds of other nuclear waste. It was in South Carolina and a pet project of a very powerful senator, Lindsey Graham, still there. It took a lot of oversight over a lot of years before something that wasn't a very good idea was finally shut down. And I played a role in that. So that's another example of the kind of work that happens.
Can I ask if the AAAS fellowship is only applicable for US citizens?
So it depends. So the AAAS fellowships, the ones that are in the federal agencies, most of those are paid for by the federal government themselves. And so it depends on the agency whether they're going to open it up to non-US citizens or not. There were a bunch of these fellowships in USAID, the Agency for International Development, which has, of course, been largely eliminated now. Those were open to non-US citizens. Many of the others, things in Department of Defense, stuff like that, are open to US citizens only with security clearance. The fellowships that are in Congress, most of those are funded by different scientific societies. And each scientific society makes its own rules around whether or not US citizenship or permanent residency is required. Beyond that, this AAAS program is being copied around the world and across many mostly left-leaning states in the country. So, for example, California and New York, Massachusetts all have programs like this where you would work in the state house as a science policy advisor. Canadian government has something similar. Several governments in Europe have something similar. So there are opportunities outside of the United States in similar kinds of positions.
I have another general question. So, how, as a science policy person, how do you work with politicians that often have the opposite view? Like, if they're opposing to what you're saying, like, how do you work with them to make better policies?
So it depends. So if there's someone that I need to work with that I think is going to disagree with some issue, then I'm going to try to make sure that we don't have that disagreement. I'm going to try to find some thread of agreement between us, and I'm going to build from that. And often, you're looking for different things. So for example, from a supporting lawmaker, you don't just want them to vote for a bill that does the thing you want. You want them to write the bill and champion the bill and spend political capital to try to get it through. Maybe someone who's kind of neutral, you want them to vote for it. But if I was talking with someone who is opposed, like I know they're going to vote against it. They have to vote against it. It's the only way that they can maintain their position given the constituency they represent. Like maybe my only ask is like, okay, I know you have to vote against it, but will you just shut your mouth? Like don't make a big speech. Don't say anything. Just make your fucking vote and move on. Like maybe that's the ask. The other thing that I think is very important, it's kind of a subtext to your question, like assumed in that was that the person who's elected is immovable. And that's not the case. If you're dealing with an elected member of government and they don't agree and they're an obstacle to getting the thing done that you want to get done, then you can work to get them unelected and get someone else elected who is aligned with your views. And I think that's the power of politics has been inappropriately neglected by scientists who somehow think that saying like, hey, we really need folks who understand and appreciate the scientific consensus around climate change, setting policy around things that impact CO2 emissions, methane emissions, energy efficiency standards, and things like that. Like, that's not particularly controversial. That's not saying we have to have a carbon tax. That's just saying that science needs to be at the table and one thing that is helped used to make a decision. That's not a highly partisan kind of perspective or anything like that. And I think advocating for that is a very valid and important part of politics as a scientist.
Okay, I'm actually. Oh, sorry.
No, you go.
Okay. I'm actually super curious about this now. You mentioned Lindsey Graham just a little bit ago, and I'm kind of curious if you could elaborate on that just a little bit, because like that of course is someone who like is sort of like one of those immovable, or at least like perceived like immovable figures, and like someone who like people like us, we would like if we ever met someone like them, like we would like really kind of butt heads with something like them. So like. I guess I sort of have this almost two-part question for you. No, like number one, did you have to personally kind of go head to head with him? And I guess how I know it wasn't necessarily like like a get a policy type thing done with him, but I guess how did you work in just that overall environment with someone that just opposing?
Yeah, so I was in Senator Ed Markey's office, so it would have never been my role to directly interact with a senator on the opposing side. That was Markey's role as the elected member of Congress. In terms of our strategy, it was pretty bare knuckles. For example, I worked out the econometrics about how expensive this fuel would be, how much it was going to cost to produce it, the uncertainties around decommissioning the plant, the more straightforward approaches to blend it down into waste glass and stick it in salt flats in Nevada. Like, I worked all of that out. And then I wrote an oversight letter to the Department of Energy, run by Steve Chu at the time. asking them questions about all of those same things with the goal of getting them on the record of saying official government policy is that this thing is not a good idea, that we're going to spend there's $1 trillion over about 60 years in order to produce $10 billion worth of nuclear fuel. So, we got the government on record saying, yes, it doesn't make sense, but this is our policy. And that kind of information became a linchpin then in a press push and kind of a shaming, like a press push. Taxpayers, you should be worried about this. A shaming campaign against the contractors who were, taking money from this boondoggle, highlighting how Lindsey Graham's job creation thing was really only creating a small number of construction jobs. They weren't even South Carolinians. And once the plant was going, it was going to be run just by robots. Basically poking holes in all of the kinds of things that were used to support it. Find other ways to build allies. For example, even if it would have made economic sense, I think I would have opposed it because the United States has long had a policy of bright line separation between commercial and energy uses of nuclear technology and military uses of nuclear technology. And blurring that line is dangerous from a global nonproliferation standard. And so we recruited people who were worried about global nonproliferation with the argument like, if the United States doesn't keep our weapons and energy programs separate, how can we ask Iran to do that or Russia to do that? So even foreign relations kinds of folks were brought over, including Republicans on it. So it's a multi-pronged strategy. Again, trying to meet folks where they are in order to find nuggets of agreement that you can build from, not just going straight into a brawl if you don't have to. But Lindsey Graham was certainly not favorable to our office.
Cool, thank you. Yeah, I appreciate that.
Any other questions? All right, well, I think we could thank Chris again for this interesting talk. Yeah, thank you so much. And yeah, I mean, if we have questions about anything about this, could we reach out to you?
Yep.
Yeah.
Please feel free to send my email around to other folks in your group.
Perfect. All right. Thank you so much.
Okay. Very nice talking. Take care.
You too.